When we're coming up with definitions and axioms and theorems in mathematics, there's this kind of meta consideration where you want to have the smallest number of extra axioms and definitions that you can get away with in order to prove the theorems you want. And so there's a theorem that we really want. If you have two lines, they intersect in at most one point. They can not intersect in any points, that's what we call parallel, or they can intersect in one point, but they can't intersect in 2 points. We want that to be true for a flat plane. And so somehow we need to prove that. And so our path to proving that two lines can only intersect in one point kind of goes through this previous theorem here. So if I think here I've got one line, and here I've got another line, and I just kind of pretend that they intersect, and I say, what's going to go wrong? If I have two lines that intersect in 2 points, what could possibly go wrong? Well, what can go wrong is I've got these intersection points. Let's call them P and Q, because I've already used A, B, C, and D. And so tell me about the line PQ. Well, I want there to be just one line that's PQ, and that line has to be L, and that line has to be M. So we want to be able to say if P and Q are on line L, because they're in that intersection, then that has to be the same as line L. And it has to be the same as line M. So this is important. I can name a line by any pair of distinct points that are on the line. And anytime I've got a line, if I pick 2 points that are on the line, I can name the line using those 2 points. And it doesn't matter which pair I pick. I always get the same line. So I'm going to try and prove that. So I start out and I think, oh, how would I prove that? Well, this is a set. And this is a set, right? And I want to show that everything in this set is also in this set. So I'm kind of working my way backwards from the end. I'd like to be able to say that this is a subset of CD and vice versa. Okay, well, how would I do that? Well, I would need a point X that's on AB. And then I want to prove that that point X is on CD. Check it out. I keep getting more and more points here. Man, I need an A and a B and a C and a D and an X. Well, it turns out that I can back this up a little bit. So I can get theorem 9 by doing some tricks. If I just have a theorem that says that if C is on the line AB, then AC and AB are the same lines. I've reduced the number of letters I have to work with at once by 1. That helps. But I still have 4 letters, so 4 variables for 4 points, because I need to say, in order to prove this, I need to be able to say if any old point is on the one line, then it has to be on the other line. So I need this. And in order to do that, I need to be able to talk about what's true when I have 4 points on a line. So my mental picture is this line, and it is named by the points A and B, and there's another point C that I'd like to be able to use to name that line. I'd like to name it AB or AC or BC or CA. And in order to write a proof about that, my set theory approach means that I have to have a variable name for some point that's just the any point on the line. So I'm going to call it X, because it's my variable. Could be any point on that line. And I need to think about what's true when I've got 4 points on a line. So what I think when I imagine 4 points on a line is I imagine them being in some sort of order. And that's where this definition comes from. It's in the set of definitions because I need to have a definition of order in order to prove that this line can have the name AB or AC or BC, any pair of points I want to pick that's on the line. And so that's why I've got this definition. And when you think about having points in order on a line and you think, oh, what order do I want to have? How do I want to define order? Well, it's defined this way with an equation about distances because that's how we defined a line. We defined a line as being something that's a shortest path. And so we want to use something that's compatible with that definition of a line for dealing with 4 points. And so we call it an order. And this is the definition I came up with for it. And it's just like the definition for a line, right? I can add up points and go from A to X, and then X to B, and then B to C. And that's the same distance as going all the way from the first to the last. And so that says these points have this order. Okay, so all of the theorems leading up to theorem 10, so from 3, 4, 5, 6, 7, 8, 9 up to 10, they are all actually little lemmas. So a lemma is a helper theorem. It's when you take an idea and you say, okay, I'm gonna package this little part of it and I'm gonna give it its own name or its own number. And so all of these are little helper theorems building up to theorem 10. That's the important famous one. And so 3, 4, 5, 6, 7, 8, 9 are kind of helping us keep everything straight on our way to getting to 10. And so I'm going to prove some of these, and you're going to prove some of these.